What if I told you that humans are on the verge of creating a tiny sun right here on Earth, a power source so strong it could provide unlimited clean energy for the entire planet? Today, we're diving deep into the fascinating world of nuclear fusion, how it works, how scientists are making it happen, and why it could change everything. Stick around because by the end of this video, you'll see how close we are to harnessing the power of the sun itself. Step 1. Understand nuclear fusion. The sun fuses hydrogen into helium under extreme heat, approximately 15 million degrees Celsius and pressure. On Earth, we aim to recreate this in a contained environment to release energy. Key challenge: containing plasma at millions of degrees. Step 2. Choose a fusion approach. There are two main approaches to Earth-based fusion. Magnetic confinement, tokamak or stellarator, use magnetic fields to contain hot plasma. Example, ITER, International Thermonuclear Experimental Reactor in France. Inertial confinement, laser fusion, use powerful lasers to compress tiny fuel pellets. Example, National Ignition Facility, NIF, in the USA. Step 3. Fuel selection. Fusion fuel is usually isotopes of hydrogen, deuterium from seawater, tritium, rare, can be bred from lithium. Fusion reaction, D plus T, He plus neutron plus energy. Step 4. Plasma formation. Heat the fuel to 100 million degrees Celsius or more to form plasma. Plasma is a state where electrons are stripped from nuclei. This requires huge energy input, often from electrical or laser sources. Step 5. Containment. Magnetic confinement. Use superconducting magnets to create a magnetic bottle for plasma. Laser confinement. Compress fuel pellet quickly to achieve fusion before it explodes outward. Step 6. Achieve ignition. Fusion occurs when energy output interfied energy input. This is extremely difficult. ITER aims for net positive energy in the 2030s. Step 7. Energy capture. Neutrons from fusion heat a surrounding blanket. Heat generates steam, drives turbines, produces electricity. Step 8. Safety and infrastructure. Fusion is inherently safer than fission. No chain reaction. Plasma cools if containment fails. Produces low-level radioactive waste, mainly from neutron activation. Step 9. Practical considerations. Cost. ITER is billions of dollars. Technology requires superconductors, lasers, vacuum systems, cryogenics. Timeline. Commercial fusion plants may arrive around 2040 to 2050. Fusion reactor accident. If containment fails, plasma touches the walls. It cools and fizzles out in seconds. No chain reaction. Unlike fission reactors, damage is mostly to the equipment itself, not the surrounding city. Worst case scenario. A sudden release of stored magnetic energy in superconducting magnets could cause a mechanical explosion inside the facility. Tritium, radioactive hydrogen isotope, could leak, but it has a short half-life and is not nearly as dangerous as uranium or plutonium. The blast would be comparable to a large industrial accident, not a nuclear bomb. Building a working Sun on Earth, a fusion demonstration, has cost so far from about $1 to $5 billion for major laser lab facilities, up to first 18 to 25 billion euros for ITER. Commercial-scale fusion power plants are still speculative, but estimates for prototype, first-of-a-kind fusion power plants range from a few hundred million to many billions of dollars, depending on the approach, size, and whether existing infrastructure can be reused. We can't literally build a sun, but we can replicate its energy via fusion reactors using hydrogen isotopes, extreme heat, and containment systems. This is the closest thing to putting the sun on Earth. If you found this mind-blowing, imagine what's next. Real fusion energy, powering our cities, ending fossil fuels, and opening doors to technologies straight out of science fiction. Don't miss future videos where we explore the incredible breakthroughs that could change humanity forever. Hit that subscribe button, turn on notifications, and join our journey to unlock the power of the sun.